do 45 minutes worth, but we should be fine with that as far as recording the lecture and posting them on YouTube. Anyway, so we're finding homes for electrons. And last time we met, we talked about, of course, you have to put electrons in subshells. And which subshell you go to next, you can know by using this arrow diagram. So I did it for you before, but I'm going to go ahead and do it here. I know this isn't in your slides. So in the margins, if you want to do this, I'll show you how it works. Okay, so we're going to go 1s. Oops, see if my pen works. There we go, 1s. And that's it. When n is equal to 2, we have an s and a p. So we go 2s, and make sure our s's line up, and 2p. When n is equal to 3, we pick up the d. So we have 3s, 3p, 3d. And if I was doing the unit exam for Unit 4, like y'all are going to be doing in a few weeks, I would put this somewhere in the margin. Then we go n is equal to 4, and we pick up the f. So 4s, 4p, 4d, and 4f. So, and we talked about there's the g, h, i, and all that, but f is as complicated as we need to get to. So after 4, now we're gonna go 5, 6, and 7. So we get to stop at 7. So 5s, 5p, 5d, 5f, and 6s, 6p, 6d, 6f, and then 7, and then 7s, 7p, 7d, 7f. And then the arrow part comes like this, where they're diagonals, so actually the first 2 arrows only pick up one subshell. The first 2 arrows only pick up one subshell. Hopefully that'll help. And then the third arrow, and remember when we start to load, it's the top of the arrow, so it's upper right to lower left. So after the 2s, we next start to find homes for electrons in the 2p and then the 3s. So we complete the diagonal, and this actually begins, I think it's the next part that begins interesting. So our fourth diagonal picks up the 3p and the 4s. So this is where if you didn't make your columns lined up very good, it gets a little hairy. And then we get to pick up 3 subshells for the next diagonal. So we have 3d, 4p, 5s. I can't read my own writing. That's supposed to be 5s. Sorry about that. And then, man, this looks messy to me. I take a step back. I'm looking at 3 again. So I'm going to go 4d, 5p, 6s, and then I get my f's. So I have 4f, 5d, 6p, and 7s, and then I have 5f, 6d, 7p, and then I have 6f, 7d, and then I have 7f. Okay. So actually at the end of today's notes at the end of part 2, I'm going to show you an alternate method of finding homes for electrons. And then sometimes I'll tell students I can put at the max of these guys, all of these s's, it maxes out with 2 electrons, right? 1 orbital, 2 electrons. We'll go back. And these 2 p's, or all of these p's, sorry, all these p's, what's the maximum number of electrons you can put in a p subshell? 6, yep. So I put 6 electrons there. How about the d? 10, perfect. And then what about the F? 14, yep. So I just kind of made it a little busier, but that's kind of what we have going on there. So kind of be able to create the arrow diagram for yourself. It's a thought. I'm always trying to kind of give hints to how best to digest material and do well on the test. So we have one more of these to do. We did atomic number 40, because I was looking at my notes. Yeah, we did zirconium, right? We found out how the electrons were configured. And now we're going to do iodine. So there's zirconium right there, and iodine is in the same period over here. So actually, do you see how this works? We could, let's see, 40 to 53, that's 13 electrons. We could actually just go back in our notes and pick up and add 13 more electrons. That's kind of how this works. Okay. but let's see how this goes. So we're going to use the arrow diagram. The first electrons are going in 1s. We're going to use the spectroscopic notation instead of the box and arrow because we would kill our hands going the other way. So we'll go 1s2, and then 2s2, and then you guys told me 6 for the p's, so or 2p6. Stay on that diagonal. 3s2. Oh, but my notes, my slides told me something special. If you ever end up with ns2, np6, that's what? 2 plus 6 is 8. So that's the octet. That's the 8 electrons that you have arrived at a rare gas. And this rare gas must have 10 electrons because we have 2, 4 plus 6 is 10. So you're at neon. All right. So beyond neon, we said the next 2 electrons go 4s. The next electrons go in the 3p. That'll be 3p6. So now we're up to, let's see, 10 plus 2 plus 6. We're up to 18 electrons. So that is actually our next rare gas in the period after neon. So that's argon. Then according to the arrow diagram, we go to 4s. And we're going to have to completely fill it, 4s2. Now we have 20 electrons. Now where do we go? 3d. And then how many electrons? Yeah, because you told me 10 maxes out, and you figured, do I need 10? Well, yeah, because I'll have 18 plus 2 is 20, plus my 10 be 30. So, yep, 3d10. You got it. Now where do we go? 4p. Yep, 4p. Yep, and how many electrons? 6. Yep, we're going to need to completely fill it. Because when I do that, we've got the 18, then the 20, 30, we're up to 36, and we're on our way to 53. So what rare gas is that like?
Oh, Christian.
Christian, very good. Now where do we go?
5s.
Yep, 5s2, perfect. I always get excited with my D's and F's because it seems so like special out there. So now where do we go? 4d. And will we need 10 electrons? Let's see. 36 or 7, 38. That'd be 48, right? So yeah. So you're looking at 4d10. So at 48, we're on our way to 53. How many more electrons do we need?
5.
Just 5. And where are they going to go?
4f.
Nope, not 4f yet.
5d.
Yep, we're going to finish that diagonal. Yep, they're going to go to the 5p. 5p5. Yep. You got it. And I think I said this before because I'm going to unscramble all these. I'm going to take a whole subshell and kind of move them around so I have increasing N. But my point I said the other day is this is great. I would leave it just like this. But if we unscramble, notice that we want to, let's see, we're fine until we get, and this is correct. There's nothing wrong with this, but until we get the 4s2, 3d10. So this guy's got to move over, this guy's got to move over, and 5s2. So this actually is in the order of increasing N. It looks like this. Do you guys have these? Okay, good. All I did was take the whole subshell and move it over. So the reason you would want to unscramble it is you would identify the highest N. And I can't remember if I said it yet, but I'm going to say it again for the first time. Our highest N is equal to 5. How many electrons are there between the 5s and the 5p? There are 7 electrons. Yep. Those 7 electrons are called valence electrons. You got it. And the best way to identify the highest N is to unscramble it. You don't have to, but okay. So, and students usually really like this, as long as you can use it correctly. There's this thing called the abbreviated rare gas notation. Most of us like abbreviated. So we were finding homes for, what were we finding homes for? Okay, ID, this guy right here. So the abbreviated rare gas notation, you use what, let's see, this period is what, period 5. You go to period 4 and you find the rare gas, okay? And then what you do is all of the electrons beyond 36 electrons, you account for them, okay? So the abbreviated rare gas notation, you can kind of flip back and forth if you want. When we had the little arrow that said KR, the rare gas krypton, we go ahead and we put that in brackets. Again, it's the period before it though. And then beyond krypton, we had, looks like we have 17 electrons. Here are how those 17 electrons are configured. Now, if you'd rather go ahead and write bracket krypton 5s2, 4d10, 5p5, that's cool too. Either way, you don't have to have an increasing end like this. Any questions about that? So on your test, when I ask you to tell me how electrons are configured, be looking for you can either write out the whole configuration or you can use the abbreviated rare gas notation. That's what this is. Okay. So far, that little case thing has not rebooted itself. Okay. So again, what does the abbreviated rare gas notation look like for saying how electrons are configured? You're going to use the rare gas that comes directly before it in the previous period. What you're going to do is put that rare gas in square brackets like you saw, and that's going to be considered the core. All right. And I've not used it, but like this last bullet says, remember the other way we can see how electrons are configured is use boxes and put arrows in them to represent electrons. That's called the box and arrow notation. You can also use this abbreviated notation with that too.
To use the abbreviated form, are we just going to have to memorize where the noble gas, like what the last segment is, or will
that's a good question. If I was using it, like in the arrow diagram, you mean kind of like, or?
I just mean like, if we're using krypton, do we have to memorize what the last set of krypton is? Like if it's 5p5.
We're actually going to get to something that's going to help you, I think, with that. But yeah, so krypton, yeah, it ended with, and I'll go ahead and tell you how this works. See, it's in period, is that 5? No, it's 4, period 4. Okay, so actually it ends in 4s2, 4p6. But you don't have to write that down. It does. I think what I would have problems with the rare gas notation is knowing where to pick up on my arrow diagram. It would confuse me. So it's just an option. But this other way I'm going to show you how to show electron configuration is actually going to be more conducive. This other way of figuring it, how electrons are configured to the rare gas notation. So this is why y'all can't use smartphones and such. There are definitely apps out there. Some of you guys downloaded a periodic table, and probably the periodic table you downloaded will show you for each element how the electrons are configured. Okay. So, for instance, this is just, if you Google electron configurations, this is what you're going to come up with. Yeah, and it's definitely using the rare gas notation. Okay. And one of my favorite, this one's just specifically for electron notation. I don't know if I showed you guys this one. It's called P-table and has all sorts of different options. And I might be going to it with atomic size and electronegativity too. But notice one of the things is orbitals. So if I click on that, that's a lot of fun too. Like if I click here, nickel, okay, nickel's got 28 electrons. Here's how those 28 electrons are configured. Isn't that fun? So, and I brought these today. I'll pass them around. I wish these would be nice to have on test too, but no. You can see with regard to what we're talking about, this side on this one, if you look real closely for each of the elements, it has the electron configuration. And then, start this one over here. This one has it like here, along with all sorts of other little interesting things. To me, the people who come up with that data must just like have, just would drive me nuts. But sometimes I feel like, you know, there's the wow of physics and the awesomeness of biology, you know, but it all kind of, there's the kind of the what do you call tedious, like the mundane almost of chemistry. Like you've got to have chemistry before you can have biology, and actually physics and chemistry intersect too. I'm kind of biased. So those are out there. Here's the arrow diagram. A little neater than the one I drew, but it's your roadmap. So I've alluded to on Friday and again today another way. This is an alternative to the arrow diagram. Do you have to use this way? No. Do you have to have a sense of what I mean by chunking up the periodic table like I'm going to show you? Yes. Okay. So here we go. You recognize some S's, some P's, some D's, and some F's. Okay. So actually, that's the S block, that's the P block, that's the D block, and that's the F block. So S block, P block, D block, and F block. So this gets really exciting. So S, you guys told me, or you know, that I can put 2 electrons in S-type orbital. Check this out. 1, 2. How many electrons can I put in a P? 6. Look at this. 1, 2, 3, 4, 5, 6. I know, right? How about a D? 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know it gets, these guys really confuse me. So F, this is F block. How many for F? 14. 14. Let's see what we got. So if we count these guys here, so we go 14. So here's the deal. When we're kind of, if your element is over here, the last to be kind of added are going to be S. If they're over here, the last to be added are going to be P, here D, and here F. So we can actually use the periodic table to kind of skip along and come up with electron configuration. The other thing is actually up here, notice that for S block, it's actually going to be, I should put an N there. For P block, it's going to be N. For D block, it's not N, it's N minus 1. For F block, it's not N minus 1, it's N minus 2. So here's all that means, where the N is actually the period. So here, if I am finding, we talked about the abbreviated rare gas notation. So if I want to pick on silicon, I could go ahead and put neon in brackets, okay? Beyond neon, I have to, my next stop is right here. See how I go 10, 11, 12. I'm on my way. What did I say, silicon? Okay. So these guys are 3s2. And then I got to skip along here, okay? 2 electrons in the 3p. So 3p with 2 electrons, 3p2. So it gets tricky. Like I'll do another one. I'll do copper. This is where it gets tricky. Because I told you, we said that these are D block, F block. But these are N minus 1. So if I'm picking on copper, I could put argon in brackets. And then after argon, so that's 18. I skip over here, I go 19, 20. So where are those 2 electrons going? That's 4, by the way. 4s2, yep. Now, not 4, but 3. So this is 3D. 1, 2, 3, 4, 5, 6, 7, 8, 9. So actually, these 9 electrons would be 3D9. See how that works? And it's consistent with the arrow diagram. It's an alternative, and it really works with the abbreviated rare gas notation. When in doubt, remember I told you what I would do is I would have both handy. I'd have knowledge of this, because I do go back and forth. Knowledge of this and my arrow diagram, so things go well. Okay. So here we go. Here's hydrogen, 1 electron. This actually is from OpenStax. You can find it in Chapter 6, Figure 30. And it kind of shows you how the electrons are loading. Okay. I think they kind of cheat because, well, for instance, atomic number 36 for atomic number 37, which is rubidium, they don't put the KR in brackets. But you guys just got to know, for instance, I have KR in brackets, then I have 1 electron in 5s. 5s1. That works. So this is the spectroscopic notation of saying how that 1 electron is hanging out. It's of course in the 1s subshell. So for most rules there are exceptions, and that even includes like the physical world, okay? But usually an exception, I'm going to show you why they occur. Usually there's a reason for exceptions. So even though on the test and on your homework, which kind of confusing sometimes, in your homework, I want you to use the rules we talked about, assigning homes for electrons. It's called the lowest n plus L subshell. Fill the subshell first, then go on to the next subshell. But I'll tell you that there are exceptions. Every once in a while, there'll be a homework assignment. They'll ask for electron configuration of something crazy, like plutonium, or platinum, excuse me. Platinum, how are those 78 electrons hanging out? Well, you're going to use the rules that we've been talking about. But there are exceptions, and actually, chromium is the first exception. And I'll show you why those occur. Okay, so if we pick on chromium has 24 electrons. And here's what you guys can tell me. How are those 24 electrons hanging out? All right, they kind of peter out. See if this is consistent with what we talked about. Chromium is in period 4. So we said, we could base it on argon. After argon, you guys see up there the 2 electrons in the 4s. And then you should see 1, 2, 3, 4. 4 electrons in the 3d, right? Okay. Well, what chromium really does is this. Let's try to compare what's different between what we think it should do and what it really does. And once you compare it, what you're going to see is this guy actually jumps ship and goes over to here. So that makes that a 1 and that a 5. And I'll tell you, I can tell you right now. So how many orbitals are there in the 3D subshell? Fingers, please.
Like possible?
How many possible places, possible boxes? Just the boxes.
Oh.
Just the 5. Yep, yeah, you can accommodate 10 electrons, but it's just 5 boxes. So the reason chromium did this, and the reason you find exceptions, is that if you completely halfway fill, if you get exactly halfway full the subshell, that's awesome too. So for that left behind, how many orbitals in an S type? How many orbitals? How many boxes? Yeah. You can accommodate 2 electrons, but if you go ahead, 1 electron is half filled.
So you have to completely fill D before you can fill the next S.
Yes, ma'am. So this, I don't want to. I hope we're all. Let's see if I can do this. Make my point here. Yep. This is exactly what you would write down, but this is what it really does. And you wouldn't have to know that. You wouldn't know that unless you memorize the table I'm going to show, or the information I'm going to show you. Yep. So why did that happen? Well, in the case we just saw with chromium, it half filled a D-type subshell. Or